In this video, we're going to go over steps on how to build our own redox table based off of data. So what we're going to do is we're going to start at the bottom of the page here because that's where all the steps are, and then we'll go back and do this example question. So steps to building a redox table. Why we would want to do that is because a redox table can be used to determine the spontaneity of reactions. Redox tables can be built by observing a series of reactions and recording which reactions are spontaneous. So when you are given a table with evidence of a reaction, so in other words, like all of these reactions where some of them are spontaneous, some of them are non-spontaneous, that is the data that we're given that we will use to build our own redox table here. So what we're going to want to do is identify our oxidizing agents and reducing agents. The strongest OA is the one that has the most spontaneous reactions. The weakest OA has the fewest spontaneous reactions. The strongest RA will have the most reactions, and the weakest RA will have the fewest reactions. So, as a reminder, when we're given a list of reactions, what we're going to do, you're going to want to highlight all of these steps because that's what we're going to go through. So, identify oxidizing agents and reducing agents. Decide if your OA is above or below the RA. Arrange the oxidizing agents in order from strongest to weakest, and then fill out the table to make them all reduction half reactions. Okay, so as a reminder before we get into this, here's the spontaneity rule. So if the reaction is spontaneous, the OA is higher than the RA in the redox table. If the reaction is non-spontaneous, then the RA is higher than the OA in the redox table. Okay, so we're going to use this to help us build the table here. Okay, so we've got our series of reactions. We're asked to build a reduction half reaction table. Now, if you're thinking to yourself, well, wait a second, in our data booklet, we have a reduction half reaction table already. Can't I just take the reactions from here and use that to build my redox table for this question? No, because most of these you're not going to see in the redox table in your data booklet. So most of these reactions will not be there. Okay, so for this, we're not going to look at page 7 for the redox table that's there. Okay, so essentially what we're doing is we're building our own mini redox table without the data booklet. Okay, so step 1, identify the OAs and the RAs. Okay, so here I'm going to focus on strontium. Okay, so I noticed that strontium has, or starts with a neutral charge and then goes to this 2+ charge. Okay, so if we're going from 0 to 2+, we're getting more positive. The only way you get more positive is if you lose electrons. So remember, Leo, the line goes grr. Losing electrons is oxidation. What's getting oxidized? That's going to be my reducing agent. So that's my RA. And then for the other one here, so we have cerium 3+, and then cerium solid. So we go from 3+ to a neutral charge. So the only way you're going to do that is by getting more negative. you get more negative by gaining electrons. Gaining electrons is reduction. Now, what type of agent is undergoing reduction? Well, that's going to be an oxidizing agent. Okay. So essentially, once you figure out one agent, which substance is one of your agents, you pretty much have the other. So you're always looking at your reactants to determine what's your Ra, what's your Oa. Okay, and whatever one you've figured out to be the Ra, the other one has to be the Oa, or vice versa. Okay, so now that we've figured out our Ra and Oa, now we look and we say, okay, this reaction is spontaneous. Okay, so what do we have to do with that? Well, step 2 says we need to decide if the Oa is above or below the Ra. So this ties into this spontaneity rule. Okay, if the reaction is spontaneous, the Oa is higher than the Ra. Okay, so what I've written in blue, if you want to coordinate it with the steps at the bottom, this is going to be step 1. Okay, and I'll write step 2 from these steps down here at the bottom of the page. Step 2, I'm going to write over here. Okay, so because this is spontaneous, our OA is above our RA. So our OA, I'm just going to be a bit more specific now. Okay, so our OA is cerium 3+, aqueous, and then our Ra was strontium. Okay. So now we keep on going and we're doing the exact same thing. Okay. So we have cerium goes from 3+ to 0. Okay, so that's getting more negative. So it's gaining electrons, which is reduction. So our OA undergoes reduction. That means this has to be our RA. So I'm just going to keep on going and figuring out what my OAs and RAs are just to finish this off. So I've got nickel, 0 charge, goes to a 2+ charge. So we're getting more positive. That means electrons are being lost. Losing electrons is oxidation, reducing agent. Okay, remember, reducing agents help other things to be reduced while it itself undergoes oxidation. Oxidizing agents help other things to be oxidized while it itself undergoes reduction. All right, so if nickel is our reducing agent, that means hydrogen, or our hydrogen ion, has to be our OA. Okay, we have platinum, goes from a neutral charge to 4+, so we're getting more positive. So you have to lose electrons to get more positive. Losing electrons is oxidation, reducing agent. So this has to be our OA. Okay, so keep in mind you might wanna double check your OA just in case you do mess up figuring out your first agent. So here we go from a 1+ charge to a neutral charge. So we're getting more negative. Okay, so we're gaining electrons. Gaining electrons is reduction, oxidizing agent. Okay. All right, let's finish off step 2 here. So this next one, so the second reaction is non-spontaneous, so our Ra has to be above our OA. So what is our Ra? It is nickel, solid. Our OA was cerium, 3+. The next reaction is spontaneous, so that means my OA is above my Ra. Now my OA was that hydrogen ion. My Ra was nickel solid. Then for the last reaction, that was non-spontaneous, so the Ra was above the OA. So my Ra is platinum, and my OA is hydrogen. Okay, so why am I making all of these notes? These are all very important background notes to help us figure out the order of everything. Okay, so for the next step, you're going to want to leave some space between what you're filling out. Okay, but I'm just going to start with the first one. So we said that we know that cerium 3+ is above strontium. Okay, so I'm going to go, let's see how much space I have. We'll say cerium 3+ is here. Okay, and since cerium is my OA, that's why I'm putting it more to the right-hand side. Since strontium is an RA, I'm going to put it more on the right-hand side. So let's say strontium is right there. Okay, so that's that first one done. Okay, so in the next one, we're showing that nickel solid is above cerium. So that means I'm just going to put nickel just above it. And since nickel solid is an Ra, that's why I'm putting it on the right-hand side. So that's done. Okay, now we're saying, okay, hydrogen ions, they are above nickel. And since the hydrogen ions are RROA, then I'm going to be putting that on the left-hand side here. So I'm going to go H plus aqueous. So that's done. And then for the last one, it's saying, okay, platinum is above hydrogen ions. And platinum is my Ra. So I'm going to put it on the right-hand side. So platinum right there. Okay, so we've got kind of the order of things. Now what we need to do, okay, is we just need to, so what we just did was step 3, arranging the oxidizing agents in order from strongest to weakest. It should say arranging the oxidizing agents and reducing agents. And then now what we're going to do is step 4. Okay, where we're going to fill out the table to make it all reduction half reactions. So down here is step 3 and step 4. Okay, so let's start with the platinum reaction here. Okay, so I'm going to put my reaction arrow right here. Okay, we know our Ra was platinum solid, but in order to figure out, okay, well, what is the oxidizing agent for this platinum half reaction, you got to go to the products here, and you got to use what's in the reactions that are given to you. So we need to use platinum 4+. Aqueous, and now we got to say to ourselves, okay, if we're going from 4+ to a neutral charge, we need to balance this reaction. We need to balance the charges of this half reaction. Okay, so remember, you always go to the more positive side. So the reactant side right now has a 4+ charge. It's more positive, right? And the product side has a neutral charge. So I need to get both of these to be neutral. So I'm going to do that by adding 4 electrons to my platinum 4+ ion. Okay, so now this is balanced because the reactant side has a neutral charge, the product side has a neutral charge. Done. Okay, for our hydrogen ions, I'm gonna line up all of these arrows here just so it makes it easy to read. Okay, so like I said, we got to go to our product side, and it's like, okay, we're using hydrogen as our reducing agent because we already have the OA for the hydrogen half reaction. Okay, so this is telling us what we need to put on the right-hand side of the reaction. By the way, the coefficients aren't coming along for the ride here. Okay, so I'm gonna go H2 gas. Okay, so now we need to balance the substances here. Okay, so I've got 2 hydrogens, so I've got 1 hydrogen on the reactant side, 2 hydrogens on the product side. Okay, so what I'm going to do is I'm going to balance out the hydrogens by rating a 2 coefficient here. Okay, I didn't have to do that for the platinum reaction because there was only 1 on each side. All right, so now looking at the reactant side, I have 2 H pluses. So in total, I have a 2 plus charge because there's 2 of these. Okay, and on my product side, I have a neutral charge. So I need to balance the charges, and how I'm going to do that is by adding electrons to the more positive side. So I'm going to add 2 electrons. Okay, also all of these are reduction half reactions, so all of the electrons are going to be going on the left-hand side here. Okay, next one we have nickel as our Ra, but we need to figure out what the OA version of it is. Okay, so I'm looking at my products, and it looks like we have nickel 2 plus. Okay, and nickel 2 plus also shows up here. So that's what we're going to be using for this half reaction. So I have 1 nickel on the reactant side, 1 nickel on the product side. So those are balanced. Now we have a 2 plus charge on the reactant side. We have a neutral charge on the product side. So I need to add my electrons to the more positive side. Now both of these have a neutral charge. Okay, cerium, let's see what we got to use. So cerium just becomes cerium solid. Okay, so over here we have 1 cerium. On the product side, we also have 1 cerium. Okay, now I need to balance the charges. How I'm going to do that is by adding 3 electrons here. Okay, because 3 plus minus 3, that's going to give us 0, and there's already a 0 charge on the product side. Okay, for strontium, we're using strontium 2 plus for the OA in that half reaction. So in order to go from 2 plus to a neutral charge, I need to gain 2 electrons. Okay, there we go. So with how we ordered this, this is how it's playing out. So our SOA is in the top left-hand corner, just like our strongest oxidizing agent is in the top left-hand corner in our data booklet. Now, as we go down our list of oxidizing agents, they get weaker and weaker and weaker. So strontium 2 plus is our weakest oxidizing agent, while platinum 4 plus is our strongest oxidizing agent. Okay. Now, this is going to follow the opposite trend for reducing agents. Our strongest reducing agent is in the bottom right-hand corner, just like it is for our data booklet. And as we go up, they get weaker and weaker and weaker. So platinum solid is the weakest reducing agent. Okay, and there we have it. So now at the bottom here, it's asking us list the oxidizing agents in order from strongest oxidizing agent to weakest oxidizing agent. Okay, so keep in mind all of our oxidizing agents, they're all on the left-hand side of the reaction arrows here. So that's where we're getting all of our chemical species. Okay, so strongest oxidizing agent, we said that's platinum 4+. Aqueous. Okay, so that is stronger than hydrogen ions. Which is stronger than the next one is nickel 2+, aqueous. Then the next one is cerium 3+, aqueous. Then the next one is strontium 2+, aqueous. Okay, so we're just following the trend that we built. So strongest oxidizing agent in the top left, and then as we go down the list, they get weaker and weaker. And this question's done right now. So let's move on here. So the next example, we are asked to build another redox table based on the reaction evidence below. Okay, so if they don't tell you anything after this, you can assume that this is a spontaneous reaction. So the first two reactions are spontaneous, but if you see this no evidence of a reaction, that means it's non-spontaneous. So these two are spontaneous, which I'm abbreviating to SPON, and then this one is non-spontaneous. Okay, so we're going to follow these 4 steps. We're going to look at our reactants, determine our OAs and our RAs, decide if our OA is above or below the RA, and arrange our oxidizing agents and reducing agents from strongest to weakest, then fill out the table. Okay, so we can make those half reactions. So let's look here. So copper 2+ goes to copper solid. So we're going from a 2+ charge to a 0 charge. So 2+ to 0, well, we're getting more negative. So that means we're gaining electrons. So remember, Leo the line goes GR. Gaining electrons is reduction. Oxidizing agents get reduced. So then that must mean lead solid is a reducing agent. Okay, for the next one, we have copper solid goes to copper 2+. So kind of the opposite of what we just talked about. So going from a neutral charge to 2+ charge, you have to lose electrons. Losing electrons is oxidation, so that's a reducing agent. So that must mean silver 1+, those ions have to be our oxidizing agent. Okay, for the next one here, zinc 2+, and we have lead. So zinc 2+, if we look at our periodic table, so zinc is right here. So zinc, if it's going to have a charge, it's going to have a 2+ charge, right? The only other option for zinc is to have a neutral charge. Okay, so if we're starting with zinc 2+, its only option is to go to zinc solid, right? That neutral charge. So that means if we're going from 2+ to neutral, we're getting more negative, we're gaining electrons, so it's an oxidizing agent. So that means lead has to be a reducing agent. All right, so let's decide if our OAs are above or below our RAs. So for our first reaction, it's spontaneous, so our OA is above our RA. So our OA was copper 2+, aqueous, and then our RA was lead solid. The next one, the next reaction was also spontaneous, so OA above RA. Our OA was silver 1+ ions, and our RA was copper solid. And then for the last one, since it was non-spontaneous, that means the Ra is above the OA. So lead is above zinc 2+. Okay, so I'm looking at all of this evidence here, and I'm thinking to myself, okay, lead is above zinc, but it's below copper. Okay, and then copper is below silver. Okay, so I'm getting the sense that copper 2+ is kind of in the middle there. So I'm going to start off with copper 2+. And since it's the OA, I'm going to rate it over on the left-hand side. So copper 2+ aqueous. And then it is above lead, so lead has to be, in other words, lead is below copper 2+. So then I'm going to put it right there. Okay, and that takes care of that. I just want to skip straight to this, but I'll come back here in a minute. So lead is above zinc, so then zinc should be right here. So that takes care of that. And now let's go to the middle reaction. So silver is above copper. So silver, there we go. And I'm just gonna scooch this up a little bit. Okay, so that's taken care of. I'm also noticing, okay, copper solid, we said that was an Ra, so I'm just going to throw that in here. Okay, so just looking at this first reaction here, I'm just going to start it off because I already have most of the information for it. So going from a 2+ charge to a neutral charge, the coppers are already balanced, so now I just need to balance charge. So I just need to add 2 electrons to make it so that the reactant side has an overall neutral charge, same as the product side. Okay, let's look at silver. So silver goes from 1+ to solid. So I'll fill that out. And then going from our reactant to our product side, we have 1 silver on both sides. So silvers are already balanced. So going from a 1+ charge to a neutral charge, I have to gain 1 electron. Okay, with lead, looks like we have lead 2+ here. So I'm going to use that here. So going from a 2+ charge to a neutral charge, we're gaining electrons, and I gotta gain 2 electrons. For zinc, like I said before, zinc only has 2 options. It's either a 2+ charge or a neutral charge. So I'm saying zinc goes to zinc solid, and in order to go from 2+ charge to a neutral charge, you have to gain 2 electrons. Okay, so remember when you're building out these reactions, always remember to include states. Electrons don't get states, but ions and solid metals sure do. So just watch out for that. You need to include states. Okay, and when you build these redox tables, it's super important that you identify your OAs and your RAs first, then make all of these background notes to yourself to help you figure out the placement of everything, and then start building your redox table. So your redox table, again, your SOA should always be in the top left-hand corner. Your SRA should always be in the bottom right-hand corner. Okay, so for the oxidizing agent, starting at the top, going down to the bottom, you start out strong, you get weak. Okay, with the reducing agents, you start at the bottom, and then as you go up, you get weaker and weaker and weaker. Okay, and there you have it.